Hello. Hello, everyone.
Hello, Laushi. How are you?
Hello, Laushi.
Nice to meet you.
Yeah, Laushi, nice to meet you again.
Nice to meet you.
Nice to meet you too, Laushi.
Last year, we have the class. Now we have another class. Okay.
Yes,
Yes,
Laushi.
Laushi.
Yeah, Laushi.
This year we have the class technical basis of mechatronics. Mechatronics. How many people select this class?
30.
30.
Yeah, Laushi. Yeah, all of them. We're in same class, so we need to select the same course.
I can see 34. I can see 34 in the last meeting.
Yes, Laushi. Yeah.
Yeah. This is the book for our class. This is our book for the class.
Laushi, do you have the PDF version of this book?
Yeah, this is the PDF.
Can you send it in the WeChat?
Okay, no problem. You are belong to class 1 or class 2?
Laushi, it's combined. It's the same class.
It's same class.
Yeah, it's combined.
Okay. Yeah. I give you the PDF version of mechatronics. You can read it by yourself.
Thank you,
And
thank you.
now I have the PPT. You can read it. You can read it. Mechatronical systems. Today we introduce the overview. Overview. Mechatronics definition. Definition. The word. Mechatronics is composed of from the mechanism and the tronics from electronics. From this is a new words. Half from mechanism, half from electronics. From here we can know this class is about mechanism and electronics. The synergistic integration is of the mechanical engineering with electronics and intelligent computer control in the design and the manufacturing of the industrial products and the process. There's three parts: mechanical engineering, electronics and intelligent computer control. Mechatronics is the application. Is the application. Mechatronics is a methodology. Methodology. So we know mechatronics are. If we think mechatronics is an application, complex decision making to the operation of a physical system, of the system. If we think the mechatronics as a methodology used for the optimal design of the electromechanical products, optimal design of electromechanical products. In the last semester, we learned something about the electromechanical. So in the mechatronics, we maybe review the electromechanical technology. A mechatronical system is not just a marriage of electrical and mechanical systems, and it is more than just a control system. It is a complete integration of all of them. The emphasis is the mechatronical system is not just a marriage of electrical and mechanical systems, and not just put them together. It's a complete integration. Mechatronics definition. Mechatronics engineering is about analysis, design, manufacturing, integration, and maintenance of mechanics with electronics through intelligent computer control. So analysis, we need to know how to analysis the mechanical products, such as FEA, finite element analysis. Design such as CAD, computer aided design, manufacturing, CAM, computer aided manufacturing, integration is emphasis, and maintenance. If we design a product, we must know how to repair it when it have some malfunction. Malfunction. If the repair is difficult, if the repair is difficult, we think the product is not mechanical, not mechanical. It's the technology about the mechatronics engineering, mechatronics engineering.
Laoshi,
Yeah.
please, what is the integration about? Is it mathematics? Integration. Just
Indication.
yes.
Indication. Indication. Just maybe like we put them together. You in me, and me in you. We can we cannot separate them. We cannot separate them. If we put them if we separate them, the system cannot work. Cannot work. Integration. This is a diagram shows the mechatronics as the center of the center of many disciplines. Many disciplines. The center is mechatronics. Mechatronics is consists of mechanical systems, electromechanics, electrical systems, controls, electronics, control systems, digital control systems, computer, and then mechanical CD. This discipline put them together, integrate these disciplines together. We can get the mechatronics. This is a mechatronics product. Aerospace, medical, extrographic, defense systems. This is a consumer product. Manufacturing. Material processing. Automotive. This is technology. This is mechatronics. This is the product of mechatronics. Product. From this figure, we know the relation, the product, the technology, and the mechatronics. Now I introduce the history of mechatronics. Mechanical engineering.
Laoshi, can you please mute? Laoshi, can you please mute all the microphones?
Oh, okay. Mechanical engineering experienced and exponential growth in the earlier 19th century, because of the industrial revolution. In the industrial revolution, the mechanical engineering growing fast. In the earlier 9th century, after that, after the rise of semiconductor, semiconductor and computer have revolutionized all engineering products and processes, which in turn affect the mechanical engineering. This is the mechanical engineering. Then the semiconductor and the computer affect the mechanical engineering. Mechanical engineering. The term mechatronics was first used in the 1960 by Japanese electrical company. Japanese electrical company to describe the engineering integration between mechanical and electronics. So this word is invented by Japanese. Since then, it has spread throughout Europe and is growing in the USA. Today, many mechanical systems use some form of electronics and computers to control its function, its functionality. Use electronics and computers control its functionality. Mechanical system engineering has gained much recognition and importance in the industrial world. Today, we know many products use the mechatronics technologies to make the product more modern and beautiful. More beautiful. In the 1960s, Japanese Society for the Promotion of Machine Industry classified mechatronics into products into four categories. Class 1, primary mechanical products with electronics incorporated to enhance functionality. This electronics just is used to enhance functionality. Example include numerically controlled machine tools and variable speed drive in manufacturing machines. Numerical controlled machine tools is typically the mechatronics product. This is class 1. Use the electronics to enhance functionality. Class 2, the traditional mechanical systems with significant updated internal devices incorporating electronics use electronics to update the internal devices significant updated internal devices. This is class 2. Examples include the modern sewing machine, automated manufacturing systems. This class 2 is higher than the class 1 is the class 1. Class 3 systems that retain the functionality of the traditional mechanical systems, but the internal mechanisms are replaced by electronics. An example is the digital watch. The old type of watch is a machine. But now the watch is a electronics product. Class 4 product designed with mechanical and electronic technologies through synergistic integration. Which means mechanical and electronic technology work together. We cannot work separately. Example include photocopiers, intelligent washers and dryers, rice cookers, and automatic oven. This keyword synergistic integration. This is a evolutionary development, historical development. Before 19th century, 1920, 1935. This is before 19th centuries. This pure mechanical systems. After the motor is invented, mechanical systems with electrical drives. This is not the pure mechanical system, not the pure mechanism. It's the mechanical work with electronics. After 1920, the Rene solenoid hydraulic pneumatic electrical amplifier. This digital product is invented. Now in the 1935, mechanical systems with automatic control. Mechanical systems with automatic control. In the 1955 and 1950 come, mechanical systems with electronic control, sequential control, In the 1975, mechanical systems with digital control, In the 1985, mechatronical systems, now is a different. This is mechatronical systems. This is mechanical systems. Mechanical systems. In the mechatronical systems, the key point is the integration. The key point is the integration. Mechanicals and electronical hardwares, and the software determine function. Software determine function. New design tools for simultaneously engineering. New design tools such as FEA, CAD. New design tools. The key points are synergetic. Sorry, it's a synergistic effect. We can see the history development. From this figure, we can see the mechatronicals is follow the electronicals development. Electronical development. The electrical drive and the auto control, automation. Increase integration of process and the microcomputer. This is a evolution of mechatronicals. Firstly, we have the mechanical systems. When we have the wheel about of the mechatronicals, we can see the two branch. This is about the control. This is about the control. This is about the electronicals. Control theories, design methodology, fault detection, discrete event theories, hybrid system theory, and decision making. As control systems used to make the decision for the control systems. As is used as software. This is the development of electronicals used as hardware. Electronicals microprocessor computer, CD systems, local network, wireless communication, and the internet. Embedded DSP, information technology. Now the electronics is combined to the information technology, information technology. Modern mechatronical systems, modern mechatronical systems. This is a modern mechatronical diagram. This is a control center. Control center. Use computer or some microprocessor to control the systems. Control system give the signal to the actuation. Give the signal to actuation, and they made the physical system work. Make the physical system to work. Then the status of physical systems is censored by the sensor. And feedback to the control center. Just like the feedback control systems. This is modern mechatronical systems. The systems can work by itself, but sometimes we need communication with other devices, so we can add the communication to the systems, and give the human machine interface to the systems. So the human can override the systems or give some reference to the systems. This is modern mechatronical systems. This is a relation about the control of mechanical systems. Control of mechanical systems. When we learn something about the control theory, we know the conception about the adaptive control, non-linear control, and the digital control. It's worked as a center. So we can use the technology in the vehicle, robots, information systems, and the motor. So control theorem is the key point in the control of mechanical systems. In the In the 21st century, mechanical engineering it will be affected by some technology, such as information technology, miniaturization, material science, by engineering and medicine, energy, transportation, environmental engineering, and manufacturing, This technology will affect mechanical engineering. So this technology will affect mechatronics. This is some example about the mechatronics. Mechatronics machine components mechatronics motion generator mechatronics power producing machine mechatronics power consuming machine mechatronics automobiles mechatronics twin. From here we can know many mechatronical systems mechatronics application area. This is automation robots, automotive engineering, computer-aided and integrated manufacturing systems, computer numerically controlled machines, consumer products, diagnostic reliability and control system technology. All this area is affected by the mechatronics. Next, I introduce the mechatronical system example, typical example, automobile. When the automobile is invented, it is a pure machine. Until the 1960s, the radio was the only significant electronics in automobiles. Radio is the only electronics. All other functions are entirely mechanical, or electrical. They work separately, not work together. Such as the starter motor and the battery charging systems. They work separately. They not work with the mechanical. Not work with the mechanical parts. Before 1960. Modeling of the combustion process shows that for the increased fuel efficiency, there existed an optimal time when the fuel should be ignited. There is a optimal time exists. The timing depends on load, speed, and other measurable quantities. The electronic ignition systems was one of the first mechatronic systems to be introduced in the automobile in the late 1970s. Electronic ignition systems. The electronic ignition systems consists of an crankshaft operation sensor, camshaft position sensor, air flow rate throat position, rate of throat position change sensor. And dedicated microcontroller determine the timing of the spark plug firing. The control is a microcontroller. The control is a microcontroller. So after the successful application of electronic ignition systems, the ABS was introduced into the automobiles in the late 1970s. ABS. ABS is used for the brake systems. Prevent the wheel is knocked when we brake the systems. The TCS was introduced in the middle 1990s. TCS traction control systems. The development of automobile nowadays, there are about 30 to 60 microcontroller in each automobiles. These processors are used for engine management, transmission control, airbags, ABS, TCS, VDC, etc. Instrument cluster, air conditioning systems, seats, mirror control, and window lift systems. These systems can work separately. Is controlled by the microcontroller. These systems are individually. Last semester, we learned something about the microcontroller. So now we can use it use it in the mechanical products. New application of mechanical systems in the automobile include semi autonomous to full autonomous automobiles. Safety enhancements, emission reduction, intelligent cruise control, brake-by-wire systems, wireless network of automobiles to ground station and vehicle-to-vehicle communication. Telematical, which combines audio, hands-free cell phone, navigation, internet connectivity, email, and voice recognition. This is as macro electrical mechanical systems macro electromechanical systems these are systems or these technologies or this technology will be applied to the modern automobiles modern automobiles This is an example for the autonomous vehicle systems weakness. Maybe you hear about the autonomous vehicle systems which means no driver in the car no driver in the car. If you want to make the autonomous vehicle systems, maybe you need add this element to your systems This is a radar is radar This is a CCD camera This is a DGPS or fog based data reckoning. If you add the radar or radar to the systems, you need a radar and radar imaging processor. Image processor. If you use the CCD camera, you need a matrix vision processor. If you add the DGPS, you need a DGPS processor. This is a sensor for the autonomous vehicle systems. Here is some other part. Maybe you need when you use in the autonomous vehicle systems. Vehicle control sensor data equation. Navigation. It's a sensory input processor. And some communication interface. From this figure, you know, if you want to make the autonomous vehicle systems, you need many elements, parts. But something maybe you know, this is just like control systems. This is a bus. This is the bus. This is a control center. This is a control center. This is a sensors give the signal to the control. Give the signal to the control. This is a computer controlled systems. Computer control systems. All these parts, all these parts will work with the vehicle. Vehicle. So from here we can see mechatronics is an evolutionary process, not a revolutionary process. The mechatronics is developed from the mechanical, so we can is a evolutionary process. Mechatronics is about the synergistic integration of mechanical and electrical and computer systems. Okay, everyone, we have a break.
Okay, last.
Okay, Loshi. Thank you.
Lashi, the break will be how many minutes? 10 minutes?
50 minutes, okay?
15.
Okay, last.
Lashi, please give us 20 minutes.
20 minutes.
Yeah, Lashi.
Okay, no problem. 20 minutes.
Thank you, last.
Kata briga, né? Nossa. Até.
Hello, hello everyone. Let's
Hello,
continue
Lao Shi.
our class.
Hello,
Okay,
teacher.
okay,
Yes.
okay.
Last class, I introduced the mechatronics and its integration. Here, I introduce the elements of mechanical systems elements. The mechanical elements includes physical systems modeling, sensor and actuators, software and data acquisition, computer and logical systems, signals and the systems. Every part has many elements. Elements. Here is a simple diagram. Mechatronics constitutes information systems, mechanical systems, computer systems, and electrical systems. Firstly, the include mechatronics is made of mechanical systems and electric systems. Now, the mechatronics includes information, computer, mechanical, and electrical. Mechatronics key elements are This is a diagram about the mechatronics. We can, from this diagram, we can see the key elements. Information systems and the mechanical systems, electrical systems, and computer systems. Information systems include simulation and modeling, automatic control, optimization. Mechatronics is the basement of the mechanical systems. Mechanical systems is driven by the actuator. The signal is come from the electrical systems. The electrical systems signal is from computer systems. So the signal flow is from the computer system to the mechanical systems to the mechanicals. After that, the signals is feedback by the sensor to the computer systems. So this is key elements about the mechatronics key element. Mechatronical systems block diagram. Mechatronical system block diagram just like the control serial. We have named in the control serial. Just like the feedback system. Just like the feedback systems. This is the end of the control systems. Signal is come from the computer or microprocessor. With the DA converts, DV converter gives the signal to the driver, and the driver drives the actuator to move the physical process. The status of physical process is censored by the sensor, by the sensors.
Laoshi, what is the full form of DA?
Sorry?
The full form of DA. Is a converter, Laoshi. D by A.
You mean DA?
Yeah.
DA. DA, digital to analog convert. Digital to analog to convert. The signal is a computer is digital, but the driver is analog signal. So from the computer to the driver, you need a digital to analog converter. This DA. So this status of a physical process is censored by the sensor, and this is maybe this is analog signal. So if the analog signal is input to the computer, you need analog to digital converter. Analog to digital converter. This is a block diagram, just like the feedback control systems. This is the feedback control systems. This is forward. This is feedback. This is the feedback. Mechatronical systems are block diagram. Here, introduce the mechatronics and the difference about the mechatronics and the multidisciplinary. The difference between mechatronical systems and multidisciplinary system is not the constituent, but rather the order, in which they are designed. The difference is the word, Multidisciplinary systems design employs sequential design by discipline. Mechatronical design methodology is based on concurrent approach to discipline design, resulting in products with more synergy. The key difference is multidisciplinary is a sequential approach. Sequential approach. Mechatronics is a concurrent approach. Concurrent approach. So we have the concluding. We have the concluding. Mechatronical systems are composed of several subsystems. Several subsystems. Mechanical, electronical, and computer control. The integration and interface among these subsystems is essential. Integration and interface is essential. Mechatronics is about the synergistic integration of mechanical, electrical, and computer systems. Mechatronical systems are at the high end of technology. This is an overview about the mechatronics. Next, I introduce the chapter 2. Chapter 2.
Can you send the PPT to the WeChat group?
Okay.
Chapter 1.
Actually, maybe for 1 and 2. Is it better?
I share the PPT in the WeChat.
OK， 老师。
Next, I introduce the mechatronical design process. Mechatronical design process. Mechatronical design process. Mechatronics is a synergistic integration of different disciplinary. We have introduced in the last PPT. It's about the electronical, mechanical, and information. Mechanical and information processing. Is a mechatronical product. The mechanical and the information process. This figure just like the feedback systems. Feedback system. This is the information process. Control center. Give the signal to the actuators and drive the mechanical. And the status is censored by the sensor and the feedback to the control center. And add the human and the machine interface to the information processing computer computer system computer It's a process about the mechanical and the information processing information processing. Something maybe we ignored when we design some mechanical products. The energy. Sometimes if you design mechanical systems, if you forgot the energy, maybe we cannot use it. But if you want to give the enough power to the mechanical products, maybe it's difficult. But the principle, the mechanical product, maybe it is simple. But if you want to give enough power, it is difficult. It's difficult. This is the difference about the conventional and mechanical design. Conventional design added component. The component is bulky. In the bulky, complex mechanisms, cable problems, and connected components. Connected components. But in the mechanical design, it is integration of components. Integration of components. Compact. The product is compact. The mechanism is simple. And uses a bus or wireless communication. Wireless or bus communication. And the systems is autonomous unit. Autonomous unit. That's the mechanical design. For the components, the difference between the conventional and the mechanical design. About the control, the control in the conventional design, the control is simple. So the structure is stiff construction. The control is feed forward control. Linear control. The precision through narrow tolerance. Narrow tolerance. Non-measurable quantities change arbitrarily. With simple monitoring, and the ability is fixed. This about the control of conventional design. Is a mechanical design. The emphasis is integration of information process. Elastic construction with damping by electrical feedback. Program feedback. Digital control. The precision through measurement and feedback control. Control of non-measurable estimated quantities. Supervising with fault diagnosis learning ability the ability of mechatronics maybe can be improved by the learning, but the conventional design maybe has fixed ability. If you want to change the ability, is complex. Is complex. Mechatronical systems integration including software and hardware integration. Software and hardware integration. Integration software is about the integration of information process. The hardware information is about the components integration of components. Multi-level control architecture. Level 1 no level control. No level control with the feedback feed forward feedback for damping stabilization and linearization is no level control for the basic function Level 2 high level control advanced feedback control strategy Level 3 supervising including fault diagnostic analysis. Level 4 optimization and coordination. Level 5 general process management. General process management is level 5. From here we can see the level is more higher. Level 1 for the basic function. Level 2 for the high level function. Level 3 for the supervising and fault diagnosis. Level 4 is for the optimization and coordination. Level 5 general process management. If you design mechatronical product, you always start from level 1. After you realize the level 1, you can go up to the level 2. Then level 3 to level 5. This is a figure about the process and the design process. When you want to design a mechatronical product, you need to think about knowledge base and inference mechanism. You need to think about from the knowledge base and the inference mechanism. synthesis product from the qualitative reasoning and quantitative reasoning. So from the two sides, you can have the qualitative optimization, qualitative design method, qualitative estimation, qualitative process model, and the quantitative optimization, quantitative design method, parameter and state estimation, and the analytic process model. This is for the quality. Is for the quality. This is for quantity. This is for two parts. When you inference the design from the two parts, you can get the basic frame about the systems. After you have the systems, you can use the sensor or feedback to the knowledge base and the inference mechanism. From the control, this control architecture, is level 1, 2, 3, 4, 5 architecture to enhance your systems. Mathematical model. Mathematical process models are for statistical and dynamical behavior. Are required for various steps in the design of mechanical systems, such as simulation, control design, and reconstruction variable. There's two ways to obtain these models. Serial model and experimental model. Serial model is based on first principles. Experimental model with mild input and output variable. This is a serial. This is an experiment. After you have the mathematical model, you can have the simulation method. You need the simulation method. Simulation include digital, analog, static behavior, and dynamical behavior simulation of the control theory. Simulation without the time limitation. Simulation, real-time simulation, and simulation faster than the real time. The three types of simulation can be used in the different products. Simulation without the time limitation. basic investigation of behavior, verification of theoretical models, process design and control system design. This is simulation without a time limitation. Just simulate the model time with the limit, without a limit, limit time. We can see the reliability of the product. We can see the reliability of the product. Real-time simulation. Real-time simulation. We can put the simulation model in the real product, real product, and find the some question when we simulate the model. Simulate the model. Simulation faster than real time. Simulation faster than real time, so we can make the real time shorter. Maybe the product work for a long time, but if we want to know the status of the product, we need a faster the simulation. Faster simulation. This is a simulation faster than real time. It's a different simulation. Real-time simulation. Real-time simulation. Real process simulation. Simulated control system. Simulated process. Simulated control systems. And the simulated process. Real control. Real control. This is real. This is real. It's 3 types of real-time simulation. Real-time simulation. Maybe process is real. Maybe control system is real. Maybe they are both simulated. Simulated. This is the hardware in the loop simulation. Hardware in the loop simulation. Hardware in the loop simulation is characterized by operating and real components in connection with real-time simulation components. Usually, the control system hardware and the software is real systems. Real systems. As used for serial products, the controlled process can either comprise the simulated components or real components. Hardware in the loop simulation. PC-based hardware in the loop simulation. This is a connection, relationship between the PC-based the software developing the PC with cross compiler, compiler. When we have the software and download to the device, and connect to the hardware, connected to the hardware with the screw term board. If you want to simulate this device with this product, you can make code on the computer and download to the DSP and control the hardware systems. If you find some problems, you can modify. You can modify your software and download it to the DSP again. Download the PSP again and simulate again. Simulate it again. Control prototyping. Control prototyping. For the design and the testing of complex control systems and their algorithms and the real-time constraints, a real-time controller simulation with hardware off the shelf signal process other than the final serial production hardware. Special ASICs may be performed, which means when we simulate the systems, we use the off-the-shelf processor, but when we make sure the control is good, we made the serial production hardware, for the product. The processor, the actuators, and the sensor can be real. This is called control prototyping. When the simulation is passed, we can make sure the control is good. Real-time simulation. You can see real-time actuates process sensor. This is real. This is simulation. But the control, the hardware and the software is real. Maybe we can use the real actuates, real process, and the real sensor for the simulation. Integrated design issues. Concurrent engineering of the mechatronical approach relies heavily on the use of system modeling and simulation throughout the design and the prototyping stages. It is especially important that it is programmed in a visually intuitive environment. We can use block diagram, flow chart, stage transition diagram, and bond graphics for the control systems. The mechatronics is a design philosophy. Is integrating approaching to engineering design. Mechatronics makes the combination of actuators, sensors, and control systems and computers in the design process possible. Starting with the basic design and progressing through the manufacturing phase. Mechatronical design optimizes the parameters at each phase to produce quality products in short cycle time. Short cycle time. It's a difference between the modeling and the experimental validation. If we use a mathematical model to predict the dynamical behavior, we can use the mathematical model. System is a validation by the mathematical model. We can, at the same time, we can use the physical systems to check the actually dynamical behavior. So compare the two results from the simulation and the real systems. So we can change the physical model. We can change the physical model under the simulate again and simulate again until the physical systems and the mathematical model get the same result. So after that, we think that we get the better the result. Get the better result. Hardware and software integration. Hardware and software integration. Hardware is about the hardware. Software is used in the information process. And worked in the computer. Worked in the computer. Concurrent engineering. Concurrent engineering is a design approach in which the design and the manufacture of a product are measured in a special way. It is necessary that the knowledge and the necessary information be coordinated amongst different expert group. The characteristic of concurrent engineering are better definition of the products without the need change. Design for manufacturing and assembly undertaken in the earlier design stage. Process on how the product development is well defined. Better cost estimated. Decrease in the barrier between design and manufacturing. This is the characteristics of concurrent engineering. As we said in the last class, the multiplanary and the mechatronicals, the difference about them is sequence approach and a concurrent approach. So this is a concurrent approach is about mechatronics. Is about the mechatronics. Concurrent engineering. We have the requirement definition. We can design the systems from quality and design for the testability, conceptual design for manufacture, marketing, industrial design, and interface design. This work is concurrent. This work are concurrent. After we have the these designs, we can integrate this together. And get the service and support embodiments and the manufacturing process So after that we can after we have the embodiment we can manufacturing the product and modify this product according to the customer or modify the manufacturing process Mechanical system design. Design is an engineering philosophy that can vary between different schools of thought. The mechanical system design is an engineering philosophy. Maybe it's that can vary between different school of thought. Mechanical systems design should follow a well-defined iterative and iterative design steps that incorporates synergetic design. It should include the following operation. One, user and system requirement analysis. Two, conceptual design. Three, mechanical software, electronics, and interface design. System modeling and simulation design. Prototyping and testing. After we have the prototyping and testing, we can back to the first and modify the design. It's the design steps. This is a block diagram about the mechanical system. This is a mechanical skeleton. This is electronical. Include sensor, signal conditioning, and the power interface. This is about the controller. This is about the controller. So if you want to design a mechanical product, you need to follow this block diagram. Think about the mechanical skeleton, electronicals, and the computer controller and the controller. Okay, everyone. Let's have a break.
Okay, Lord.
Thank you.
Okay, Lord.
Okay.
Gì đi
Hello.
Hello，老师。
Yes，老师。
Yes, 老师，老师。
Hello. Let's continue our class.
OK， 老师。
Okay.
Okay, 老师。
Mechatronical system design mechanical system design when we design the mechatronical products, we need to think about the mechanical skeleton electronicals and the controller the specific part in this block in this block for example the active edge uses electrical pneumatical hydraulical the electronicals are real part about the position sensor, the speed sensor, the temperature sensor, and the pressure. The signal conditioning. Signal conditioning include the amplify ADC fields. ADC fields. Power interface include the H-bridge circuit, pump, power operation amplifier, OP-AMP. The controller includes the computer, PLC, and the embedded system, embedded systems. The next, I introduce the steps. In the design stage, in the design stage include stage 1, stage 2, and stage 3. Stage 1 defines the objective and the specification. Stage 2 analyze and design. Stage 3 build and test. Firstly, introduce the stage 1. Define the objectives and specification. Identify the program, research and literature review. Set the initial systems specification. Identify the program. When we want to design products, we need to know what kind of program about the product. We didn't know problem. We need to check the look for the research and literature which has been done by other people. And give the system specification. Give the system specification. It is before we do the product. Before the design. Before we design the product. This is the stage 1. This is stage 1. Stage 2. Analyze and design. Establish a general block diagram and a flow chart. Specify system I/O. Specify control algorithm to use. Step 5. Choose appropriate components are choose this is choose sensors, actuators, controllers, drive and signal conditioning circuit choose concurrent synergistic design concurrent synergistic design mechanical structure, electronic systems, software, and the controller interface. This is a difficult part. It's a difficult part. Model and simulate. Model and simulate. This is the stage 2. Stage 2. Stage 2. Stage 3. Stage 3. Emulate the controller hardware. Emulate the controller hardware. Build a prototype. Test and evaluate. Modify if needed. If needed. This is a stage 1, 2, 3 for the mechanical design. Mechanical design. Includes 9 steps. 9 steps. 1, 2, 3, 4 to 9, and 8, 9. 8, 9. 再来，logistic logistic design logistic design mechanical design, electronic design, and software and control design system design and design integration This logistic design is about the step 6. Step 6. Mechatronic design process. Mechatronic process. We can follow these steps with this stage. With this stage. This process is consistent to the stages. Recognition of the need, conceptual design, and functional specification. First, principle modular and the mathematical modular. Sensor and actuator selector detailed modular mathematical modeling. Control system design, design optimization. After this modeling and the simulation is finished, we can build the prototyping. Build the prototype. Build the prototype. We can simulate hardware in the loop simulation. Hardware in the loop simulation. After that, we can design optimization. Optimization. If the product is verified, we can deployment of the embedded software and check the life cycle. Check the life cycle. This is a cycle. After that, we can back to the design and modify the product. Modify the product. This is a mechanical design process. Mechanical design process. This is a process from the we model MSD from Association of German Engineer Guideline. German Engineer Guideline. Systems design, system integration, system design and system integration. This is a process. This is a process. Computer-aided systems. This is important features. Important. These are the important features. Computer-aided systems. Computer-aided modeling, simulation, project management, and design. This all is include computer-aided systems and computer-aided systems. Modeling, block diagram for working with understandable multidisciplinary models that represent physical phenomena. Physical and phenomena modeling. This is modeling is mathematical modeling. Mathematical modeling. Simulation. Simulation. Numerical method for solving models containing different discrete linear and nonlinear equation. Nonlinear equation. After we have the model, we can transfer the model to the mathematical model or the numerical method. With the numerical method, we can simulate the model. Simulate the model. Project management. When we design the mechatronics, maybe there's many data. We need a database for maintaining project information and the subsystems model for eventually reuse. Design. Numerical methods for constraint the optimization of performance functions based on model parameter and signals optimization. Design optimization. Design optimization. Next, computer-aided systems include analysis, real-time interface, code generator, and embedded processor interface. Analysis, frequency domain and time domain tools. Frequency domain and time domain analysis. Real-time interface. A plug-in card is used to replace the part of the model with the actual hardware by interfacing to it with actuators and sensors. Code generator produce efficiency high-level source code. From the block diagram. We transfer the block diagram to the source code, such as C or C++. The control code will be compiled and used on the embedded processor. On an embedded processor. Embedded processor interface. Communication between the process and the computer-aided prototyping environment. These are the computer-aided systems are included in the mechatronic design process. So if you want to do some design for the mechatronics, maybe you need to learn many softwares. Mechatronics key elements are information systems are mechanical systems are electrical systems are sensor and actuators are real-time interface are information systems include all aspects for information exchange. Signal process control systems and analysis technical. The following are essentials for mechatronics application. Modeling and simulation, automatic control, numerical methods for optimization. System information, information systems. Information system modeling. Modeling is the process of representing the behavior of a real system by a collection of mathematical equations and logical. A collection of mathematical equations and logical. Models can be static or dynamical. Static models produce no motion, no heat transfer, flow, traveling waves, or any other changes. The dynamical models have energy transfer, which results in power flow, Dynamical model have energy transfer. This cause motion, heat transfer, other phenomena that change in time. Models are cause and effect structure. Cause and effect. They accept external information and process it with their logical and equations to produce one or more outputs. Parameter is a fixed value unit of information. Signal is a change unit of information. Models can be text-based programming or block diagram. If you wanted to know some specific information about the information systems, maybe you need to learn MATLAB. This software. MATLAB. This is mathematical software. Mathematical software. We can use this software. Build the mathematical model. Mathematical model. Information systems are simulation. Simulation is the process of solving the model and is performed on a computer. Simulation process can be divided into three sections. Initialization, iteration, and termination, The key elements are information systems include modeling and simulation. Mechanical systems mechatronics key elements are mechanical systems. Mechanical systems are concerned with the behavior of matter and the action of force. Such systems are categorized as rigid, deformable, or fluid in nature. Rigid bodies assume all bodies and the connection in the systems to be perfectly rigid. Do not deform. Fluid mechanics are consistent of compressible and incompressible fluid. Newtonian mechanicals provides the basis for most mechanical systems. And consists of three independent and absolute concepts. This is about the Newtonian mechanics. It's absolute concept, space, time, and mass. In the Newtonian mechanics, the space, the time, and the mass is never changed. Force is also present, but is not independent of the other three. Mechanical key elements are electrical systems are concerned with the behavior of three fundamental quantities charge, current, and voltage. Current and voltage. Electrical systems are consist of two categories. Power systems and communication systems. Power systems may be the power is bigger than the communication systems are. An electrical circuit is a closed network of paths through which current flow Circuit analysis is the process of calculating all voltage and currents in a circuit, given as it is based on two fundamental laws. Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law: the sum of all current entering a node is zero. Kirchhoff's of voltage law: the sum of voltage dropped around a closed loop is zero. Electrical system power. The energy is the capacity to work. Various forms of the energy include potential, kinetic, and electrical, heat, chemical, nuclear, and radiant. This is the various form of energy. Power is the rate. Of energy transfer. And in the SI unit systems, the unit of energy is joule. And the unit of power is watts. A watt is 1 watt is 1 joule per second. This is instantaneous power. Instantaneous power. P is equal to V times I. This is time averaged power. Time averaged power is integration in the time 0 to t. Key elements sensors. Sensors are required to monitor the performance of machines and the process. Common variables in mechanical systems are temperature, speed, position, force, torque, and acceleration. Important characteristics are the dynamic of the sensor, stability, resolution, pricing, robustness, and the size and the signal process. This is the important characteristics. Common variable in the mechanical systems. The important characteristics are intelligent sensors are available, but not only sense information but press it well. Intelligent sensors sense information and process it. Progress in semiconductor manufacturing technology has made it possible to integrate sensor and the signal processing on one chip. Sensors are able to ascertain condition instantaneously and accurately. This sensor fascinates operation normally performed by the control algorithm, which include automatic noise filtering, linearization, sensitivity, and self calibration. Sensor now use the intelligent sensor. Actuation involves physical action on a machine or processor. They can transform electrical inputs into mechanical inputs, mechanical outputs such as force, energy, and position. Actuator can be classified into three general groups. One electromagnetic actuators, such as AC, DC, electrical motors, stepper motors, and electromagnets. Group 2 are fluid power actuators. Hydraulic, pneumatic. Unconventional actuators, such as piezoelectric, and magnetostrictive, memory mental. This is a through general group. Piezoelectric. When we give the force on the piezoelectric part, we can get the voltage. On the piezo electrical part. Otherwise, if we give the power to the piezoelectrical part, we can get the give the force to the give the power and the voltage to the piezoelectric. We can get the force. This magnetostrictive, which means if we give the magnet give the magnet to the material. We can change the long length change the length of the part. We can change the length of the part. It's a memory mentor. Can remember the initialized sharp. Remember the initialized the sharp. After the force out force is released, the mentor can back to the initial sharp. Initial sharp. This is a special unconventional actuators. Sorry, everyone is here.
Yes, Laoshi, we're hearing.
Yes, Laoshi.
Yes,
Maybe you are tired.
Yes, Laoshi.
Yes.
Yeah, and we are also hungry.
Yeah, this is our
You're
first class,
hungry.
Laoshi.
You can ready for your sample. Okay.
All right, all right.
Okay. For today's class, we can finish it. Okay.
Okay.
Okay, Laoshi.
Okay. Maybe this class is difficult, but I hope you can read the book I give you. Okay.
Yes,
Okay,
we
Laoshi.
will understand.
Okay.
Okay. So much for today. So much for today.
Okay, thank you,
Okay,
Laoshi.
Laoshi.
All right, Laoshi. Bye bye.
Okay. Bye bye.
Okay, Laoshi.
Bye.